So students, next topic of our discussion in machine learning course is about the nonlinear hypothesis, and we will be focusing over here on neural networks. So if you remember last time even we discussed some of the nonlinear models or hypotheses. So if you remember, we discussed H is it has got some lower order terms, okay, and then it has got some higher order terms, for example theta x square, x2 square or something like this. So these higher order terms, they made the equation overall a non-linear equation, which is not a straight line, and it makes it complex. Now here we will discuss it further with a different angle, different view. So if you remember, this was the case we saw over there in the case of classification and the cancer data set. We saw these higher order terms were over there in the hypothesis equation. So these higher order terms that we got over here, they represent over here, they are based on very many different features. So maybe we can have 100 features. Out of the 100 features, we can have a lot of different terms created by the mix of these features. Maybe we have x2, then x2 is mixed with x1, x2, and then it can be x1 square, x2, and so on. So this thing makes it complex overall and non-linear. Overall, when you have these terms that are higher order terms, they will make the overall computation more time consuming. So those of you who have already taken the course on algorithm analysis, so it will be that average 5,000 features, maybe with these complex terms it can take a time of up to O of n square complexity. But when the features are more and you have bigger data sets, then it can even take much higher time complexities, which is O of n cube. N cube is a polynomial time complexity, and it is quite costly. Now we will discuss over here one new angle of discussion. You see over here this image, it is about, it's a car, okay. So previously you saw over here there were the two classes we wanted to classify based on two features. So feature was maybe, so this example is maybe the house you want to buy or not, or this house will sell easily or not. Okay, so this is a classification, it's not a regression problem. Okay, so there is one feature x1, there is another feature x2. Similarly over here we have got a car, and let's say we focus on a small area of the car. So you see over here a small area which is the door handle of the car. For us, we can easily recognize it, we can see this image, but for the computer camera, it sees it like these numbers. Clear? So it sees this as set of numbers. So all of you who have taken the computer vision course and they are coming over here, or they are taking it in parallel and they are over here, it will be more interesting to them, this topic, because over here we will be dealing now with some sort of computer vision application also. So we have got this data, which is a set of numbers which is scattered around x and y axis. Okay, so this data, this represents my picture. Okay, so based on this data, I can have many examples that can have the same properties. For example, you see over here the cars. All of the cars, they have some sort of black area or black pixels that are related to the tire. Okay, so there are some black pixels related to the tires, all of them. Okay, and then there are some other features that are, so black pixels are over here also for the motorcycle also. Okay, but they are not over here in the building. or in other animal pictures or scenery picture, they are not there. But there are black tire pixels in a truck, for example. So if you keep on adding these pixels up, okay, so let's say you take your logistic regression classifier and you want to train it on, for example, the whole picture. Same size pictures, thousands of same size picture. Maybe this picture, let's say it's a 50 by 80 size, okay, and you train your model to classify this these images, okay. And what you want to do is that each picture, it is different from others. So all these pictures, they are different, but they will have some things that are common. For example, the handle of the door that you saw in the previous example, then the tires, okay, maybe headlights, I don't know, okay. So many things, they will be common in the cars. The pixels, they will have almost similar values in many different pictures. The car is old or new, but still they will have many things in common, okay. So these 6 examples you see over here, they will have those things, all of them will have those things in common. Those pixels, they will have some common values, okay. So let's say you track only 2 pixels for now, okay. So let's say we track 2 pixels only. One is over there on pixel 1 and the other is pixel 2 near the tire, okay. And I make a graph over here only for 2 pixels just to give an idea, okay. So these 2 pixels, they have the same color, they have same maybe high value or whatever you can say. They have same values for these 2 cars, okay. So pixel 1 is high, pixel 2 is high. For the white car, pixel 2 is more higher and pixel 1 is maybe a little less, okay. So these 2 images, they are close to each other. Whereas the scenery, it will definitely be lacking these values, okay. And also the well image, it will be lacking these values. So what happens is that if you take thousands of such examples, many past examples of different images, the important point is the images are different, they don't share anything common, okay. So in that case, what will happen when you have lots of images and you try to train some sort of classification model, maybe a logistic regression? What will happen is that those pixels, only 2 pixels we consider over here now, but let's say you have 1000 pixels, I cannot make a graph for them, okay. Maximum I can have is a 3D graph. More than 3 dimensions, I cannot make a graph. But it will have a similar behavior. The pixels, the more the pixels are, they will have some sort of pattern. The items that are similar, for example, the cars, they will tend to be together, near to each other, okay. And the other items, they are not same as cars, they will be at the other side of the graph. And definitely there will be special cases. Maybe there will be a fire truck, there will be motorcycle. Many things will be on the boundary or they are misclassified. There will be some examples, okay. So if you go back, the last one, so in this diagram you see there were 6 car examples, okay. So these car examples, they will lie in the positive area, in somewhere close to each other, and they will be in the positive side of the classification. Whereas these others, they will be in the negative side. Some of them will be highly negative, like this scenery, like this dolphin, like these buildings. But some of them will be maybe in the boundary area or like neutral. Okay. So based on this, you can make a classifier that will finally, after you do the training, that will finally have a boundary. It will have some sort of boundary. Okay. So it will have a boundary, and when you give it a new picture in the future, which is not any of those pictures you gave in the past, it is something totally new. But still it has many common things like the pixels here, like maybe the door handle. So because of those common things, it will happen that when you try to classify it, it will be classified somewhere over here and it will be classified correctly as a car. So this is one of the most important uses of machine learning that came in the early days of its invention. So almost you can say 12-15 years ago, this was one of the initial uses of AI. I will give you one more practical example, highly practical and very important example. Okay, so this was it, what we did, and make sure you understand this concept that pixels, we use them as input features, X values, and we use lots of pixels, but the only difference as compared to the last approach is that in the housing prices problem, maybe we had 10-20 features or maybe maximum 100, but now it is difficult. Now it is that we may have 1000 pixels. So pixel number 0, every pixel is one input feature and it can go to millions. Remember, normal images, they are in millions, but remember, if you try to classify a big picture, a database of big pictures on your normal computer, it will take too much time. Be careful. So each pixel, it behaves as a separate one object, and each picture will give us one row of data. So each picture will give us one row of data and the output is same. Is it a car? Yes. Is it not a car? 0. So picture 1, picture 2, picture 3, like this. Clear? So maybe the picture has 1000 or 1 million pixels. They will be inputs and the output is only one value, car or not car. And each picture, each new picture will be one entry or one instance of the database, of the table. So here is an example. Let's say if we have pixels, a small image of 50 by 50. 50 by 50 is a small size. I think it is like this, not bigger than this. Small image. It will have 2500 pixels. So this small image, even it has a lot of pixels. So these 2500 pixels, and it is for grayscale image. If you consider a color image, then remember from your media computation course that color images have 3 different matrices, R, G and B, 3 channels. So then it will become 7500 values. So all of them, for now, just consider this simple case, 2500 pixels. We put them over here like a vector. So it will give me 2500 values inside the X matrix, and then I will use it to train my output. So each value is between 0 and 255. So features, they can have a lot of different features. We can have, if I am using quadratic features, then I can have up to 3 million features. Why? Let's say leave theta 0, maybe theta 1 can be with x1. Then I can have x1 coming with square. Okay. So, and then it can be in the combination with another feature, maybe theta 3, so x1, x2, and so on. So there can be so many combinations possible. So on the average, maybe if you have 2500 pixels or 2500 features, you can multiply one coefficient with all other coefficients, and you can have up to 3 million features. So you can see, just imagine how quickly these things become complex, too complex. Okay. So for this purpose, we will be discussing over here a new technique which is different from the ones that we saw previously. It was a new topic and very interesting topic. It's called the neural networks. Neural network is the a new or different approach in machine learning, and it is based on the human brain. So let's first go through a little bit of biology of the neurons and the human brain, how it works. So neural networks, its work was originally done based on the algorithms to try to make such algorithms that can behave like human brain. There was a lot of work done on this thing in the 80s and 90s, but at that time suddenly there was like people call it the AI winter. So in the 90s, late 90s, there was AI winter when everything related to artificial intelligence was going down. So neural network was part of that, and there was no interest in it. Later on in 2000s, I think 2004 or 5, came some of the interesting applications of neural networks. We will see we will see them over here also. So one of them was image recognition, the handwriting recognition. Okay. So one part of the human brain, if you already know that in the human brain there are different parts. Okay, there are many blocks in the human brain. So I don't know exactly, but there are many different regions that are dealing with different types of functions. For example, maybe one block is dealing with the eyesight. One part of the brain is dealing with the speaking power. Okay. Another part of the brain, it is maybe working with the maybe eyesight and speaking, and there can be another one which is with the movements and so on. So let's say this part over here, it is mentioned, it's related to listening. So auditory cortex, it is related to listening. Okay. What the scientists, they did some experiments. So the link is given over here for a research paper. So you can search it on the internet. You will get the information. This was some interesting work that was done by some research scientists, that what they did was human brain, the listening part of the human brain, it gets some signals from the ears. Okay. So now some people who had problems with the listening and who had problems with vision, what they did was that if you remember, the human brain, it connects to the whole body through nerves. What are nerves? Nerves are these small wires that pass the messages from the human body, whole body, they pass the messages to the brain. For example, when we feel pain, for example, in our hand, it is the nerve that carries that feeling of pain to the brain, and brain will get this feeling, and we have this notion of pain with us. Okay, it is one of the medicines or the injections that the doctors give, that this nerves, it disconnects or sleeps temporarily, and when they are operating, or they are, for example, doing something with the hand, they cut and they make some incision, and we don't feel any pain. So it is because of these nerves that we have the feeling. If the nerves are not working, or they are sleeping or dormant, then we will not feel pain. So what these research scientists, they did was, the nerves that were coming from the ears carrying the listening signals, they disconnected them and they rewired the nerves that were bringing signals from the eyes. And one interesting thing that happened, that the brain that part of the brain that was dealing with the listening, it so it got signals from eyes. That part of the brain, it started slowly, it learned slowly to see. Not a perfect vision like our human eyes, but it started to see. Clear? Another experiment was done related to touch. So this part of the brain, it is related to touch sensors. So signals come from the outside related to touch, and they rewired or reprogrammed it to get the input from eyesight. Okay, so some serious experiments have been done. You will see these links over here, and they are not so old. So 2005, 2009, 1997, these are the research works done. So for example, you see over here, a person is seeing with his tongue. So information is provided for the visual through the sensors on the tongue. They are fed over here, and from this tongue they go to the brain, and brain decodes it. And interesting thing is that the camera image that comes over here, it goes to the brain, and brain can decode it also. You can see, and it was a very important development, especially for a person who has problem with the vision. Remember, the experiment over here, it is not something a perfect result. It gives a very blur type of image that the person can see. Similarly, there were other experiments like some devices that can give humans the feeling like a sonar. The sound wave that comes back after reflection, they can feel it. And they also provided some sort of belt that can give the feeling about the directions for blind people. It's very useful invention that blind people, they will get directly, their brain will get feelings from this device about their direction. Clear? So these were some of the uses of the applications that they tried to do by modifying the function of the brain. Now, why we studied this? We studied this all because neural networks, they are created based on the idea of human brain. But so here it is, the human brain, it contains lots, you can say millions or even trillions of small these cells. We call them neurons. Okay, so a neuron is the basic unit of human brain, and it has a nucleus. So this is like the thinking part, and it has got many branches. Okay, so the branches next to the nucleus, they are called as dendrites, and there is one main branch that is going somewhere else. This branch is called as axon. So these dendrites are basically like input wires. They are getting the input from many different places. Nucleus, based on those inputs, it makes some sort of decision, and it provides the decision on to the output, which is axon. So axon is the output wire, and dendrites are the input wires. So you have to memorize this idea, these three things, very important. So neuron, it has got three main parts: nucleus, dendrite, axon. Clear? So axon is like the output, and there are millions of such cells that are connected to each other inside the human brain. So there is one neuron over here, it's connected over here. So these are the inputs coming. So many inputs are coming from different other neurons, and one output is then passed on to another neuron as an input. So this output over here is one of the input, and there are many other inputs from others. So like this it works. There is a huge network. I literally said to you earlier that there are billions and trillions of these cells. So they are connected together, and they are passing quickly these electrical signals, and these signals, they are transformed with the help of these nucleus. So nucleus, it will get some input, it will generate some output in the form of signal. And finally, one of such a signal then, based on these neurons, is some signal then goes to the human body, different parts of the human body, to make some decision. So maybe one of the signal, the one that was coming from the eye, it was coming over here, and then from many different neurons, the output comes over here to this neuron, and this neuron, that is the one that controls the human muscle movement part. So this is the idea how the human brain works. Same is the concept that is taken in the neural networks. So neural networks is based on human brain or human neuron. The idea is that there are inputs, several inputs. Let's say for now we consider only three inputs. These three inputs, they come to the nucleus, and nucleus will do some sort of calculation based on the three inputs, and it will produce some output or not. So output is like 0 or 1. Okay. So these inputs that are coming from there, they are basically our features. X0, X1, X2, X3, which we saw previously also, same things as in the housing prices problem or any other problem or breast cancer problem. These are the input features. Then each input feature that is coming from there, it has some sort of weightage multiplied before it is given to the nucleus of the neuron. So this is the weightage that comes. Okay. Then there is one unit, one extra input that is coming from the x0. And if you remember from your logistic regression or linear regression, x0 gives you the intercept. It is like your theta naught will be multiplied over here with x0. So x0 is some input that is always 1, and it is multiplied by the theta. So basically theta value is the one that you feed over here. So it's we normally call it the Bayes term. It is same as in your logistic regression. You had the term without any input variable. It was your coefficient, pure coefficient, or the y-intercept in the case of linear regression. Okay. So all these values, they come to the nucleus, and over there in the nucleus there is one extra thing that is done, is there is an activation function. The input that is coming from the previous values, it is transformed using sigmoid. So remember the sigmoid. So we saw the sigmoid in the logistic regression chapter. Same is over here. The inputs, they come, they are passed or treated by the sigmoid function. So over here you see theta x is passed through this function to get our h value. So h is nothing but the g of z, which is the sigmoid getting the value from x and theta. So overall our theta values, they are our weights or parameters, and we do some sort of calculations. So this is the model of a very simple or the simplest neuron model. What happens is sometimes you need to make your model more complex to cover more complex cases. If you remember, like in the cancer detection data set, you may need sometimes that your decision boundary is complex. So in that case, what we do is we add one extra layer. So these layers are normally fully connected. Fully connected means that x1 over here is connected to everyone in the next layer, and then x2 is connected to everyone, and then x3 is connected to every other. But in the final layer, every element in the before layer, it connects to the final layer. Okay, but remember there cannot be any connection between layer number 1, for example, and layer number 3 or output layer. No, it's not possible. This is not allowed. Only the adjacent or next neighboring layers, they are allowed to connect. Clear? And again, same important thing, other than the first layer is the input. Other than the input layer, all other layers, whatever value comes from whatever value comes as input, it must pass through sigmoid function. Okay, same sigmoid over here also in the output also. So here it is, and then there is a one bias term. Bias term is always 1. This extra layer I add between the output layer. So output layer has only one element. For now we consider the case of one element in the output layer. This is and then the input layer is the first layer. In between the layer that I added, we normally call it the hidden layer. Hidden layer, we call it hidden layer because everything it hides everything. It is hidden from both the input and the output. Input does not know that there is a layer and how many elements or how many nodes are in that layer. Similarly, output does not know about this layer. They don't know. It's like a black box. That's why we call it hidden layer. Or another meaning can be like, if you look from the outside, no one can know in this neuron how many hidden layers are there. For the outside world, only 3 inputs are there and there is 1 output. They don't know what is happening inside. And remember, inputs, they are fixed. So it depends on your features. For example, output is 1, okay, but the number of nodes in the hidden layer, they can be many. It is very possible that you can have many nodes, for example 5 or 6 or 7, but same case, if there are multiple nodes, every other node in the previous layer will connect to them from the previous layer. It will connect. Clear? You can pause it here and you can go through it and discuss with each other also and ask questions in the group. I will appreciate. So here you see. So this calculation, leave the calculation part. It will be huge calculation. But just what they are doing is that g, if you remember, it is the sigmoid function. To the sigmoid function, I am passing these values. Okay, what is the value that is being passed over here? It is the uh, theta matrix. So this is capital theta, not the small one, and it is the matrix of weights that are over here for the input values coming. Okay, and it is multiplied with the inputs that are coming from the previous part, and finally these theta. So you see theta 10 is multiplied by x0, theta 11 with x1, theta 12 is with x2, and 3 and x3. So it's a simple calculation. First node x1, it will be multiplied by theta 10. Okay, so all of them, they are passed to this. Then the nodes in this layer, nodes are given some name, for example a1, a2, a3. These we can call activation of this unit I in layer J. So effectively at each layer we are performing two types of things, two types of functions. One is the getting the inputs from the previous layer and then aggregating them, and then the second step is passing them through the activation function. So basically the first step that is occurring over here, it is basically the same thing that we have seen earlier in many different places related to, for example, logistic regression or linear regression, when we used to create the hypothesis or the model. So we have, for example, theta 0, then theta 1 multiplied with the first input, and then theta 2 multiplied with the second input, and these thetas, they can be many. Okay, So it depends on, we can use combinations also. We can have another theta, for example, and it's multiplied with the combination of first and second. Okay. So something similar is happening over here also. Every input contributes to every element of the network. This type of networks over here, they are also called as, there is a name used, fully connected networks. Fully connected. So here what we see is that x1, or from here we will like to see the this node over here. So these over here we call them nodes. So this node, it gets an input from x1 and x2, x3, all the previous inputs. It is getting one input, and for each input there is a multiplying factor, there is a weight. So for example, the x1, we would call it, because this is a1, so we will call it from, it is the value that is coming from 1 to 1. The next one, we will call it the value that is coming from 2 to 1, and this will be theta 3 to 1. Similarly, the ones that are coming here for the third, it will be theta 1 3, 2 3, and 3 3. Okay, so this is how it continues. It will keep on it will keep on growing like this. So this will be a very dense or heavy mesh of or network, and we will have these things. We will have the A, which is the activation of the unit layer I. So here it is, the hidden layer that is in the middle. Each one will have an equation like this. So it is basically the sigmoid function, and in the sigmoid function we provide like this the values. So here they have used different numbers. They are starting with 0. So 1 0, 1 1, 1 2, 1 3. So it's the opposite they use. Sorry. So here they use 1 0 coming from the first. Maybe 1 0 will come from there, from the bias node. 1 1 means this is the first node and the value is coming from 1. Then 1 2, 1 3. So this is the theta, this is the input, this is x2 input, and theta is 1 2, third input 1 3. Similarly over here it's 2 0, 2 1, 2 2, like this. So the summation that you see over here, it's linear. Yes. So it is linear function that we have over here, but the g function over here that you see, that is not linear. If you remember, g is sigmoid, and sigmoid is something like this. Okay, sigmoid is not linear. So linear are the functions which are straight line, where behavior is exact straight line. I give you some point on x-axis, you can predict what will be y. For example, I give you two example that this is x and this is y, then you can predict in the future what will be x and y. So similarly here, but for the sigmoid, its behavior is not linear, it's different, and as you go increase the value of x, it slowly becomes close to 1 and then it's fixed. So that's why the layers over here and each of the node in the layer, they are not linear. Okay, and effectively overall the output that you will see over here, even though we are using simple linear equations, so you see, you will not see over here complex equations, complex terms in the equation. You will not see x square or x cube, or no, it will be simple equation, but still the overall effect of the neural network, it will be complex, non-linear. Why non-linear? Because of the sigmoid function, non-linear. The overall effect will be non-linear. It can classify, for example, two classes with a very, very complex non-linear boundary. So this thing happens, it continues from first to second layer, and then from the second to third layer. It is the same principle. So here we will have, for example, theta 1 0. So there is only one node over here. So remember, over here they have given the node numbers. So this is 1. Over here it was 1, 2, and 3. So here we have only first, you see this one over here, it shows the node of the current layer. So in the last node over here, in the output node, there is only one element, one node. So there will be only one over here. So 1 0 into A naught, 1 1 into A1, then A2, and then A3. So it will be combined together and it will give me our hypothesis function. So this is the summary of the neural network. Maybe it's little confusing, but that for that reason we will explain how people have done it, how what efforts were done to make it simple. But we will take a small example which is very simple to make it easy to understand. So this is about the dimensions of the size of the theta matrix. So we will show you over here the representation. So this is another one. So now I will also we will discuss about the complex forms where we will have more than one layer. So this you already know. All these things that you see over here in a very complex form, practically they are represented when they are used in the programming. So programming is used to solve these models. Normally it's done very easily by using the matrices. So all these x values over here you see x0, x1, x2, x3, all of them they are over here represented by one x matrix, which is like a column matrix, which is like a vector, and it has four entries x0, x1, 2, and 3. Okay. On the other side, then we have similarly, so here you see the theta matrix that is used. So theta multiplied by x, it gives us the z matrix. Okay. So these details, leave them for now. Just you should understand it, but I don't think you at this stage need to go into these details. But you should know the formula that it's linear. So here is an example. One is input layer, hidden layer, output layer. Input as output layer is always there. Hidden layer you can have, or you can have no hidden layer. You can have 1, 2, 5, 10, up to you. Okay. For each layer, the previous layer, it knows only about the previous layer. It does not know anything about what is happening behind that. For example, for this node, it only knows about this layer. It does not know anything about the first layer. So this is the principle. Okay. Sometimes there can be more than one layer in the middle. All of them, they will be called same, hidden. Okay. So they will be called hidden layer, and they can have different number of elements. For example, over here you have 3 nodes, here you have 2. You can have 10. You can have 5 nodes in the first and then 10 in the second, or you can have 2 and 20, or 3 or 100. Any combination is possible. There is no restriction. In the hidden layers, you have no restriction on the number of elements. It depends on you, and it will affect your result. So always the machine learning engineers, they are testing and they are trying different number of layers, different number of nodes in the layers to find the best match for their results. Normally, one thing very important, when the number of layers are many, okay, in the hidden layer, this type of network, this type of machine learning, it is called as deep learning. I don't know if you have heard this name anywhere before. Deep learning. Clear? So here are examples. These examples will make the things more easier, I hope. So let's say you want a non-linear classification. Okay, so remember the word non-linear. Non-linear, why I say non-linear? Because if you see, there are two classes given over here. Input is x1 and x2, and the output is you see this red cross and the blue circle. You want to classify it. Can you classify it using a straight line? No. If you try to draw a straight line, any straight line you draw, it cannot classify it. Okay, it is not possible. So what we will do for that purpose, what we have to do is we will be using some sort of non-linear boundary. So x1 and x2 over here, they are binary in this case. Now this example is something which is from your logic design course. It's called exclusive or exclusive NOR gate. So remember at that time, if you don't remember, just let me draw the. So if you have a simple logic gate and it has two inputs, it can have four possible values. Remember, 0 0 0 1 1 0 1 1. Okay. Now these inputs, when the gate is XOR gate, what will be the output? So exclusive OR gate will provide you an output something like where is it? It's not given. So exclusive OR gate will give you an output, I think, like this: 0 1 1 0. So it will make the output as 1 if any one of them is 1, but it is not an OR gate. It will make it 0 when both of them are 1 or both of them are 0. This is exclusive OR. Okay. So this is what we want to create over here. How to do this? It is not possible to do it simply or directly. So we will discuss it over here, and same principle can then be used when you have more number of input values possible. Here you have only two possible values for x1 and x2. Either it is 0 or 1. But if you can have multiple values, you can use the same principle. Non-linear classification. Okay. So here it is. We want to perform exclusive OR. So first of all, we will start. Exclusive OR is a little bit complex. We will start with a simple AND gate. All of you remember what is an AND gate? AND gate will provide you the output when both the inputs are 1. So it is 0. Only for the last case it is 1 when both the inputs are 1. That is AND gate. Okay. So we have got over here an input layer and one output layer. So there is no hidden layer. It's a very simple neuron. So we want to keep it simple. And how it will work, we will discuss over here. Just so this is something that is only given for the purpose of making things clear to you. Okay, so this is not something very serious. It's not something very important. So here you see the weights are given for each of the input. One input is added over here extra. This one is the bias input, and it has always got a value of 1. Okay. Other two are the inputs that you have in your model. So you have two inputs from the model, and one is the bias input. And so bias is something that you try to add yourself to give it an extra value. Just like in the case of equations, you have the y-intercept value, mx plus b. That b is same as this thing. So here we add it. So it has a 1 value and it is multiplied by some weight. Weight can be changed, adjusted. Okay. So the task of the problem is that we adjust these three weights so that the output is correct. So Over here you see the weights we gave already over here. These weights are given, and these weights make it an AND gate. How? We will see. So let's say the input is 0, x1 is 0, and x2 is 0. 0 multiplied by 20, both the cases it will be 0. 0 and 0 is 0, and the third input is minus 30. It will be always minus 30. So what will be the result? Result will be the summation, sum. So it is basically the sum layer. It will sum them up and then it will pass it to the G. So sum of this thing will be minus 30. Minus 30 will be passed to the G. And G is sigmoid. If you remember, what does sigmoid do? Yes. Sigmoid value is a function where its value crosses 0 at 0.5, and if the value is on the negative side, it will make it almost 0. If the value is on the positive side, it will make it almost 1. Clear? So what will be the result over here? Because the value is negative, it's very high negative, so it will become 0. So that's what is happening over here. G of minus 30 will be 0. G of minus 10 will be 0. G of minus 10 again. Last case will be different. Why? Here I have got 1. X1 is 1 and X2 is also 1. Both of them are 1. So over here at the input, the summation, the terms will be plus 20 and plus 20. It's 40. 40 minus 30 will give us plus 10. So plus 10, when it is passed through the G sigmoid function, it will give us a 1. Clear? So this will happen, and what practically, so this is the sigmoid shown over here. What practically happens is that the behavior of this hypothesis function h, it will be same as x1 and x2. Here, this will be our simple AND gate. With little bit of changes. Now this is the beauty of the neuron. Remember, we discussed previously that the human brain, scientists, they did experiments with the human brain, and the part of the brain that was related to listening, if it was given the input from the eyes data or a camera data, that part of the brain started to feel the seeing data. So that part of the brain started helping in seeing. Similar thing can happen over here, that the inputs the weights you have over here, the weights that you have got over here, you can so we have got over here the weights. Now these weights are different. How much different? You see, it is 20, 20, same as the previous case, but here we have, instead of minus 30, it is minus 10. And this change in the weight over here, now you will definitely ask me from where these values are coming. That will come later on. For now, just imagine you know this magic. Okay, so when this value changes from minus 30 to minus 10, now this behavior of the neuron, it has changed from AND to OR. Now it is an OR gate. How? Let's see, let's try. So you give it over here 0 and 0. So here you will have 0 and 0. Okay, 0 and 0, you add it with minus 10, it will give you minus 10 as output, which will be a 0. Okay, whereas in all other cases, one of them is 1. For example, this one is 1 or that one is 1. The value that comes here, it will be 20 minus 10, which is 10. Okay, so 10 is positive number, it will give you and the sigmoid output will be a 1. It will happen in both these cases, and in the fourth case it will be even higher value. It will be 40 minus 10, which is 30. It will also be a 1. Clear? So this is what will happen, and this is the representation of the OR gate. So with little changes we make over here the AND gate and the OR gate. Another example, this time there is only one input and we can make a NOT gate. If you remember NOT gate, what it is, the input is 0, the output will be 1, input is 1, output will be 0. So NOT gate, remember for each neuron there must be one bias term. So this is the bias term, the 1. Okay. So bias term, and the other is the input over here. When the input comes, the input passes over here. What will be the weights selected? So again, the weights we will discuss how they come like this, but for now the weight over here for the input term is minus 20 and the bias term it is plus 10. Okay, so you can see that bias term is important everywhere. It helps us a lot. So we select these weights, and what we do is that we pass it the value when it comes. For example, when the 0 comes, then there will be a 0 over here, but the overall sum will be plus 10. Whereas if there is a 1, the overall sum will be minus 10. So plus 10 is 1 and minus 10 is 0. This is how it works over here. Then we get a NOT gate. So we have seen that we can create easily with little bit of with little bit of changes. We have created 3 different types of gates over here: AND, OR, and NOT. So this is the hypothesis function that's shown over here. This is the value that comes. So this time it is 10. Now the hypothesis over here is shown like this. It's the linear hypothesis. You see, simple linear equation. 10 over here minus 20x1. Okay. Only thing that makes this whole hypothesis non-linear, because remember, a linear function can only do linear things. It can never do non-linear things. So even if you have 10 linear functions, they will have cumulative effect as linear. So if I have many layers and each layer is doing linear, each layer has a linear model, the overall effect will be linear. It can never be non-linear. Okay, but because of this, only this sigmoid, this is very important, sigmoid function, it makes it non-linear. So here you see the result. This over here we are using not x1 and not x2. I think it is NAND gate. Yeah, this is NAND gate. Not x1 and not x2 is a NAND gate. Let's try. So not x1, where is this input? Yeah, it is the opposite of AND gate. So remember, what is the AND gate? AND gate is 0 0 0 1, whereas the NAND is the opposite of AND. NAND means not AND. Okay, so not AND, what happens is it is the output 1 0 0 0. No, it's not NAND. The NAND will be 1 1 1 1 0. This one, this is NOR then. Yeah, NOR. OR gate is 1 1, no, 0 1 1 1. So it is 1 0 0 0. So this is NOR gate. So they haven't shown here. It is a NOR gate, this one. Okay, what they want to do, they are creating some new gates. There is OR already with us, there is an AND already with us, and we also created the NOT gate. and here now they have got is a NOR gate. They have created a NOR gate, and what they have done for the NOR gate is that they have attached the input is inverted. I don't know if you remember this or not. If you invert the inputs x1, x2 and pass it to the AND gate, it will become NOR gate. Okay, I think we used to draw it like this. If you have an AND gate like this, okay, and if you so I don't remember exactly, if you make invert the inputs like this, two inputs with bubble, it is basically same thing as NOR gate. So this is OR and this is it. So just go back or check it on somewhere on the internet, or go back and check your books in logic design somewhere. You will find this theory that inverted input AND gate, it is same as NOR gate. So they have created over here NOR gate with the help of AND gate and NOT gate. Okay, so why they created a NOR? Basically, remember, their target is to create this thing, which is the exclusive NOR. So exclusive NOR they want to create, and exclusive NOR is something like this. So the one that I showed you previously was XOR. Exclusive OR gate was that one. The output is 0, 1, 1, 0. Whereas the one over here they want to make it is exclusive NOR, which is the opposite of this. It is 1, 0, 0, 1. And they make this gate with the help of other gates. Okay. So exclusive NOR, they create it with the help of AND and OR gates. So here it is, you see. Now you see the exclusive NOR gate, the behavior is more complex, and they create this behavior with the help of uh, extra layers. So now one layer is not enough. So what they do is over here they have got the AND gate. So you see same number of inputs are there. Okay, so same number of inputs are there with this x1, x2, and this is Bayes term. And first of all they are passed to this red node, and this red node is basically what it is doing is it is giving us the AND gate. Okay, AND gate, it creates the AND gate, and then there is another input coming from the same x1, x2 and Bayes term, and this time it gives us the output, which is the NOR gate. So one node is AND and the other node is NOR. So this is what is happening. The other one is NOR, and finally we pass on these values to the next. And remember, every time we pass on and we go to the next level, we will add this Bayes term again ourselves. So every layer, so this thing is called layer. Okay, that was input layer, this one, and this is the hidden layer. So each layer will have its own Bayes term except the last layer. Last layer does not need any Bayes term because last layer is providing only one output. There is no other output, and Bayes is not needed. All other layers, including the input layer, will have a Bayes term. This plus one. So here it is. These two gates, one is AND gate and NOR gate, they are combined over here for the output, and they provide us exclusive NOR gate. And how it works, you see this red one over here, it's the AND gate, and this cyan color, this is giving us the other one, the NOR gate, and then we are just combining them together. The values that are used over here, minus 10, 20 and 10, 20, these are the same values for the OR gate. We are just combining them. We are not doing anything else. So what is effectively happening is that there is an AND gate, and there is an AND gate, and there is another one which is NOR gate, and these two gates, their output is combined to create the output, final output. This is what is happening. So practically there are three gates that are created over here, and three gates are created by three set of values. So this is gate number 1, this is gate number 2, and this over here is gate number 3. One is AND gate, number 2 is NOR, number 3 is OR gate. That's what is happening over here. AND, NOR, and the last one is OR gate. You feel free to pause this video, go through these details, and I request you that without looking at the slides, just draw the notes and try to play with these values. Don't see at these weights, and try to judge these values yourself, and where you can create an output gate. A simple gate has come in the exams many times. Either it's quiz or final exam, it has come many times that you are asked for any simple gate. I never gave a two-layer gate before, but any gate is possible in the exam. So you just have, what you have to do is that you just pass on, you just play with these values. For your exam, you should be able to create any gate. So there are so many gates possible. So there is, for example, AND gate, there is NAND gate, there is OR, there is NOR, NOT. All these gates you should be able to draw in the exam, and you should be able to draw it more quickly. If you don't practice in the exam, maybe you are sitting 1 hour thinking on these values, which is not good. Okay, so practice it. Try to make sure that you understand these concepts. Very important. This is the basis of the neural networks. So here it is. When the neural network layers, they are a lot, we call it deep learning. Okay, remember this important point. When the hidden layers are a lot, remember input and output layers are always there. So when they are a lot, we will have a deep learning. Now let me show you a little bit of practical usage. In almost 2005, I think, this neural networks, they got a lot of appreciation, because one of the papers, I think it was by scientist Jean LeCun, who gave this work. He presented his work with this in the AT&T research, and they gave this idea that millions of letters, thousands or millions of letters are posted every day in America, the postal letters, and on the letters, so on the envelopes, the address and postcode is written by hand, and there were a large number of staff that was arranging those letters by hand. When they had to, for example, one set of letters will go to one city, another set of letters will go to another city. So he proposed over there that the writing the digits postcode. So for example, if you know, yes, for Brahmi the postcode is PC 512. Yes. So they said that they make the program that can easily scan the numbers on the letter, and accordingly they can arrange the letters automatically. And they first demonstrated it in 2005 successfully, and it was very successful. And now at the present time, most of this task in the US Postal Service, it's done by automatically, it's done by machines. So here is an example. So this is so this is Jean LeCun's work. You can search more about it. It was handwriting digit recognition, handwritten digit recognition. Next week we will discuss it. I want for all the students to come together, and we try to make a similar program for Arabic digits recognition, whatever is the style, writing style used in Oman related to that. So we will discuss it in the next week. So here you see different types of writings that are possible. So the writings is shown over here. The one that's on the side, it's shown the different writings. They are on, for example, a plastic film, and they are shown to the computer program one by one, and computer program will detect whatever it is over here. So you see, for example, it detects a 0. So this 0, you see, it's handwritten, it's not perfectly written, still it recognizes it quite correctly. Okay, so I think there is a video for with this. Let's try. Yeah, there is a video. We can try it. So I suggest you people to play it at your computers also. It is quite an interesting idea. So it's a 0, 1, 2. It's easily recognizing every one of them. This is 3. Now you see over here the 3 written, it's extremely in bad shape. Even I think it's not so easy for a human to comprehend it as proper 3, but based on the proper training, it's easily recognized as 3. So 8 is recognized even if it's written as 2 separate circles. Now there is noise in the numbers. You see lots of noise, background noise. Maybe page is old, or there is some dirt on the page. Still, it can recognize these digits. These are, by the way, same ideas that are now practically employed everywhere, even in the Muscat airport. Here in the Wadi Jizi, all these things are now used over here also. The same ideas. So these are three numbers, 3, 8, and 4. So this was the idea. So this was the idea for the use of neural networks for sort of image recognition. One more thing is similar as in the logistic regression. Here we can also have multi-class classification, and it is also done on the same principle as over there we saw previously. We do it one versus all when we want to classify multiple things. For example, there is a huge neural network and we want to train it for four things, to detect four things: some person walking, pedestrian, car, motorcycle, or a truck. So in that case, what we do is that we have a neural network that the output layer for which has got four nodes, and every time when one of these is detected, only one output is having a one value, others are zero. Okay, so for example, pedestrian, it is 1 0 0 0 and so on. So this is how it happens. One node for one item. The rest of the behavior is very simple. All these nodes are trained such that they give a voting for each thing. So the voting occurs, for example, that all the nodes, they give over here a vote for the next layer, and these nodes over here, they vote, for example, for one of the four outputs. When they see a pedestrian, most of them, they try to vote for this node. When they see a car, most of the nodes, they try to give vote for this and nothing for the other nodes. So this is how it happens. So in this type of classification, we don't use the numbers. For example, for the output 1, 2, 3, 4, no. We use this type of, it's a very common word used over here. It's called one hot encoding. So one hot encoding is used over here, where we are using the output will have the values in binary only, and one value represents one class. So you can study more about this thing on the internet, one hot encoding. So in this chapter over here, we don't discuss anything about how these models are trained. That is way beyond the scope of this course. But the theory is same over here also. When we train the model, we train it using the same concepts of gradient descent. And these model parameters, these theta values, they are changed or tuned slowly based on the feedback of the value of the j, the cost function. So all the theory is same, but we don't consider here for deep learning, which is quite difficult as compared to others. So with this, we terminate over here. We finish our lecture on the deep learning.